Good morning. Well, looks like we'll be going online for a while. I don't know if for 2 weeks or maybe even till the end of the course. So I'll be working under the assumption that we will go online until the end of the course. So that is my current plan, is to try to work online till the end of the course. Again, we will start classes with the Kahoot or a quiz, which we'll do online, and we can all enter online together. I'll then move forward in the class in introducing the general ideas using our physics website. After our physics website introduction, we will then hit on with some PowerPoints. I'll try to pause at certain times to allow you to think about things and try to answer the questions that are on the PowerPoint. I'm sorry that we'll not be able to get too much response this time, but this is the way we'll try to do it. So today we are currently working on thermodynamics, 热力学. This is something that you did not study in high school, so will be quite new to you. But it's a very important topic, especially for electrical engineers. In the first semester, we've talked about energy. In particular, we've talked about transfer of energy using work. We've always mentioned that the other way in which energy can be transferred is heat. So in thermodynamics, we are discussing energy transfer by heat. And as you are probably aware of, that is one of the key problems or difficulties as we try to shrink the size of circuits. And in electrical engineering is how do we deal with heat generated by our circuits? And in the production of electrical power, we often are trying to change heat into electrical energy. For example, in Taichung with the coal-fired electrical generators, this is basically a transformation from the chemical energy stored in the coal into heat, which is used to create the steam, which is used to create mechanical energy, which is transmitted into electrical energy. So a key part of this is the heat aspect. And that is what we're going to be trying to study in the next few weeks. Okay, so I hope you enjoyed the guided discovery, thinking about thermal, that you did yesterday. Today, I'm going to spend one lecture discussing the macroscopic description of matter. Next week, we will have 2 lectures, both focused on the heat and the first law of thermodynamics. We will then spend 1 lecture discussing the micro and macro worlds. And then we'll spend a couple of lectures discussing heat engines. We will then, if necessary, we'll add an extra lecture here. If not, we will then immediately go to our guided discovery on 20th century physics, followed by our milestone on magnetism and milestone on thermodynamics. So if this 3rd lecture is needed, we will give it. If not, then we'll try to move the course up by 1. There'll be a milestone must-see retry on either the 23rd or the 24th. So that is our plan for the next few weeks. If everything is online, we'll be moving through with them all online. Again, you'll be responsible for doing the pre-reading before the class, the assignments after, and basically the Kahoots during our class time. Let's now discuss today's lecture, A Macroscopic Description of Matter. Okay, so we've been looking at physics so far in terms of a particle model, where we've assumed in the last semester, you assumed that everything was basically a point particle. But now we're trying to look at macroscopic things. Real things have volume. They have a specific size. If it's a gas, it has a pressure. Of course, it has a mass, which we've already discussed, and everything is at a certain temperature. We measure temperature, which is related to the thermal energy of our system. So, and finally, another parameter is the density, which is the mass divided by volume. So in thermodynamics, we are looking at basically 4 state variables are the key things that we look at. Volume, pressure, if it's a gas, the mass, the temperature. Basically, these 4 variables are important. In addition, when we're looking at a macroscopic description of matter, it is also useful to consider the number of molecules. Now, because there's so many molecules in a typically sized piece of matter, right? If your cell phone, for example, if we tried to count how many molecules are in the cell phone, we get a very huge number. So, in order to simplify this, we talk about moles. So, if the number of molecules is n, there is a number, Avogadro's number, Na, which says that we will assume that 6.02 times 10 to the 23rd molecules equals 1 mole. Okay, then we can divide the number of molecules by this number and say, okay, we have 6 moles of molecules in this cell phone. Why do we want to do this? Convenience. Easiness. It's much trouble to say, I have 3.6 times 10 to the 23rd molecules here. It's much more simpler to say, oh, there's 6 moles of molecules here. Okay, so the definition for moles is just to simplify and make the numbers of a similar size. If you have one number that you have to always multiply by 10 to the 23, it'll be okay with calculators, but before calculators, it'll be kind of troublesome. Okay, so the number of molecules are going to be related to the mass of a material, as well as the weight of an individual molecule. All right. A next thing that we're going to be introducing in this chapter, which you've already seen a little bit, is the idea of phases and phase diagrams. The crucial point here, as you discovered, is there are 3 basic phases of matter that we're going to be discussing. There are more, but we're only going to discuss 3 in this class. Liquids, okay, like water between 32 degrees and 100 degrees. Solids, water below 0 degrees becomes ice, so it's a solid. And gas, again, that would be water in our world above 100 degrees C. It's steam, okay. So if we looked at this as what, we can then draw how these states of a substance, for example, water, would exist on a graph. This graph, the x-axis is temperature, the y-axis is pressure. Okay? So, if we have low pressure and higher temperature, we will get a gas. Okay? If we have a low temperature and a high pressure, or any pressure almost at low temperature, or here higher pressure, we will get a solid. If we have a high temperature and a high pressure, we will generally get a liquid. Okay, so these will be the 3 phases of diet. So for example, if I'm at the atmosphere, okay, let's say I'm in the atmospheric. Okay, let's say my atmospheric pressure is here. So if I'm very cold, I will have a solid. As the temperature increases, it will stay solid until it hits 0 degrees Celsius. When it hits 0 degrees Celsius, my solid ice will become water. As the temperature continues to increase, it reaches 100 degrees Celsius, it will now become a gas. Okay? So that's how we would follow this diagram. Or we could say, well, let's say I've got this temperature here, I've got a relatively cool temperature, but I've got a very low pressure. Okay? I'm below atmospheric pressure, so I start at, say, 15 degrees, but very low pressure. I'll start with a gas. As I start to increase the pressure, I will become a solid. Okay, and this is special for water. If I keep increasing the pressure, I will at some point be able to go back to become a liquid. But that is very unique for water. Only water can do that. Now you can see these lines on this graph. These lines show the change where the change occurs between gases and solids, or gases and liquids, or liquids and solids and liquids. In English, we have some specific vocabulary. If a solid becomes a liquid, it is said to melt. If a liquid becomes a solid, we say it freezes. If a gas becomes a liquid, we say it condenses. If a liquid becomes a gas, we say it vaporizes. Now, if a gas becomes a solid, we say it sublimates. If a solid becomes a gas, we also say it sublimates. Yes, English is a crazy language. Yeah, to say that a solid sublimates to a gas and a gas sublimates to a solid doesn't really make too much sense. I think in chemistry, you studied in high school the idea of the ideal gas law. So if I looked at this PT diagram, it's this corner where you can use the ideal gas law. PV equals nRT. I think you guys would have learned it that way, or it could have been PV equals KB, KB NT, right? So one of those two ways. But you know, this law is only valid in this small area of low pressure and high temperature. Other ways, it's not. So let's look now again in more detail this ideal gas law area that we learned before. First of all, the ideal gas law is based on two incompatible assumptions. Incompatible means if A is true, then B cannot be true. If B is true, then A cannot be true. So what are the incompatible assumptions? The assumptions that can't be true at the same time, that are the basis for the theory. The first one is molecules never touch each other. In other words, this molecule will never bump another molecule. Okay? In other words, so the pressure is so low that the molecules will just go freely and never ever see another molecule. The second assumption is that for this ideal gas law is that they're in thermal equilibrium. Thermal equilibrium means that basically there's a specific distribution at the same temperature and it'll be a Gaussian distribution. Now, if a system wants to go to thermal distribution, thermal equilibrium, molecules must hit each other. Remember our laws of momentum. M1v1 plus M2v2 equals M1v1 afterwards plus M1v2 afterwards, and we had conservation of energy. So if something going fast hits something going slow, what happens? Well, in this sort of a transition, the one that's going slow will be able to go faster, and possibly the one that's going fast may end up going a little bit slower. So they'll come more to thermal equilibrium by having contact. But the assumption of the ideal gas law is that this will never happen. But surprisingly, even though there's two incompatible assumptions, it works. The ideal gas law works. Where does it work? away from the phase transition boundary. You can see there's no transition boundary anywhere near this ideal gas law. It's quite a ways away. Okay, so the equation, as we showed in the diagram, is PV equals nRT. This is how the physicists often write it, in where R is 8.31 and N is the number of moles. So they're nice small numbers. Now, if you are a chemist, they often write it PV equals NKBT, where KB equals 1.04 times 10 to the minus 23. So you get a huge number of N and you get a very small number of KBT. So these are both a big number and a small number multiplied together, 10 to the minus 23s. Well, physicists like to use numbers between 0 and 10. So 8.31 and some number between 0 and 10. So physicists like to use moles, while chemists are just using number joule K minus 1. So the units joules, energy per Kelvin, and here we have moles. All right, that's the PT diagram. Now, for one specific type of process, okay, that was a PT diagram. Okay, now let's move on to the PV diagrams used to illustrate the ideal gas law processes. Okay, now note, this is pressure versus volume, not pressure versus temperature. Okay, so when we're talking about ideal gases, we often don't plot them as PT diagrams. We plot them as a pressure versus volume. Now, if we know pressure and volume from this equation, we know temperature, right? If there's the same number of molecules, we know R is a constant, number of molecules are the same. If we know the pressure and the volume and the number of molecules, we can also give you the temperature. Okay, so it's not like this diagram is losing any information. So from the PV diagram, we can get the temperature. But generally, we are only interested in changes, okay? And we also make the assumption that everything changes very slowly for these sort of things. Okay, so let's look at the different types of transitions on a PV diagram that we're going to discuss for an ideal gas. One is called isochoric. Isochoric. So for isochoric transitions, that means the final volume equals the initial volume. There's no change in volume. So if we look at this graph, the P versus V, it's got to be a vertical line. So either we can be going from low pressure to high pressure without changing the volume, or from high pressure to low pressure. These are both called isochoric. The next one is isobaric. In an isobaric transition, the final pressure equals the initial pressure. In other words, it's a horizontal line. So the volume changes, but the pressure doesn't. So for example, we can go from a small volume to a big volume at constant pressure. Okay, or we can go from a big volume to a small volume at constant pressure. Now, and the final type of process is an isothermal process. In other words, the final temperature equals the initial temperature. In other words, there's no change in temperature through the whole system. So in order to do this and draw this type of one, the isothermal processes go on sort of you can see it's not a straight line. Okay, it's a curve on this guy, either going from so both the pressure and the volume change, but the temperature remains constant. So isochoric, volume remains constant, meaning you've got a vertical line. Isobaric, the pressure remains constant. So you've got a horizontal straight line. Isothermal, the temperature remains constant. So in all these cases, once we have this PV diagram, we can tell the temperature just by plugging in the initial P, V, and R. So if you look here at this isobaric one, you can see the volume is increasing, but the pressure is staying the same. What does that tell me about the temperature? The temperature is also increasing, right? because volume is increasing, the temperature increasing. This one, the volume is decreasing. If the volume is decreasing and we're at constant pressure, that means the temperature must be also decreasing. Okay? Here's when we're increasing the pressure. If I increase the pressure on something and I'm squeeze it more and more tighter together, what happens is I keep the volume the same. I'm wanting to increase the pressure. What have I got to do? If I heat up the material, that means the pressure will increase. If I keep the volume constant and I cool it down, right, the pressure is going to decrease. So this is how PV diagrams are used to illustrate the ideal law process. So let's quickly summarize then one more time. The state variables are volume, pressure, mass, and temperature. We also are concerned about the number of molecules, which we often specify as physicists as moles for convenience, so we don't have to use big numbers with 10 to the 23rd. We talked about phase diagrams, which are generally plotted as pressure versus volume. And we have three basic phases: solid, liquids, and gases. Within these phase diagrams, there's an area which is covered by the ideal gas law. In this case, we can use a PV diagram to illustrate the ideal gas law. In the ideal gas law, temperature is related to pressure and volume and the number of molecules.